This is the first homework help video for Chapter 4 in Statistics on Probability. I want to start off with an example of how work should be shown in this chapter. In this chapter, you're going to be dealing with a lot of fractions, and I would like to see the fractions. For example, here we're going to compute the probability of drawing a face card and then drawing a 10. So here's one probability, here's another, and in this particular case, because of the and, we multiplied the two probabilities together. This is actually all the further you have to go in a test. On homework, you can get the calculator and go ahead and find that it's 1.8%. But I need to see these numbers because otherwise I don't know how you even did the problem. So homework starts with the formulas and notation of probability. Anything that you do, any experiment, will have a certain outcome. Those outcomes are called, or the group of outcomes is called an event. And in probability, we denote it by capital letters, starting usually with the A in the alphabet. So you have event A, event B, event C. The complement of event A is everything in your experiment that could have occurred except A. In a Venn diagram, that's usually shown by a square. The square supposedly encloses all of the possible events in your experiment. And if we show A as a circle, which is common, then the complement of A, which is written A with a bar over it, is everything outside of that. For example, if your experiment involved drawing an ace of spades, okay, the complement of A is everything but the ace of spades. If you're in your experiment, your event A is drawing a pair of dice and getting a 12, then the complement of A is throwing that pair of dice and getting anything but a 12. Alright, so in this chapter, P of A means the probability that event A will occur. This notation is a probability of event B, and the vertical line in here is read as given. It's a probability of B given that A has already occurred. For example, if I'm drawing cards out of a deck, if I've already picked one card, the next card's probability depends upon that. Because, for one thing, there are fewer cards in the deck, and second, it may have reduced the number of count of the particular cards that you're looking for. So this is read probability of B given A. In this class, we're going to work with two formulas concerning the combinations of two events, A and B. One is A and B, and the other is A or B. A and B means that event A and event B either occurred simultaneously or one right after the other. Or means event A occurs or event B occurs or both of them occurred. This is what's called the inclusive or. If you go into logic and into electronics and switching and gating, you will study the inclusive or, which is what we have here. There's also an exclusive or, which means either A or B, but not both together. So this is your inclusive or, and that is a question on the homework. Oops, need a pen. So it's the inclusive or. An example of A or B could mean you want the dress to be red, or you want the dress to be green, or it's okay if it's both red and green, like red and green stripes. So or means either A or B or both of them together, and means A and B occurring at the same time or simultaneously. I mean, that's simultaneously, or one right after the other. Now note here that and in arithmetic is associated with addition. 3 and 4 means 3 plus 4 in arithmetic. In probability, and is associated with multiplication. So this is probability and associated with multiplication. The or is associated with the addition. So that's a little different. Once you see that, then makes it a little easier. Okay. Now if we're looking also at events A and B, there's two characteristics of them that are important. One is that they're mutually exclusive or not, or if they're independent or dependent events. If events are mutually exclusive. It means they both can't occur at the same time. For example, if you're looking at the probability that you're broke, either you're broke or you're not broke. You can't be both broke and not broke at the same time. For independence, the probability of one event has no bearing on the probability of another event. For example, the probability that you get fired has no bearing on whether the sun will come up in the morning or not. Those are two separate events, and their probabilities have nothing to do with each other. Those events are considered independent. Now, dependent events might be coming into work late and then getting fired. That could make a difference there. So the probability of B getting fired might be greater if you came into work late, given that if A was the event that you came into work late. Now we'll compute some specific probabilities, and there's a procedure for doing it, and it's fairly straightforward. Let's say you want to find the probability of drawing a specific card from a standard deck of 52 cards. If you play cards very much, you know there's different kinds of decks, but we'll always be using the standard 52 card deck. Right. Now, if you want to find the probability, you first count up all the number of occurrences of that specific type, and you put that in the numerator. Then you divide by all the available cards. In this case, 52 would go down in the denominator. So say you want to draw an ace of spades. Well, there's only one ace of spades in the whole deck, so the number is 1, and 52 goes down here. That's for the ace of spades. Say you just want to draw an ace. Well, there are 4 aces in the deck. 4 over 52. Now let's look at the probability of throwing a specific number on a standard die. I know the word die is a very awkward word, at least it is for me, for using it to be half of a dice. I'm used to saying pair of dice. Dice is the plural, die is the singular. So we have a standard die, meaning it's got 6 sides. So to find the probability of throwing a specific number, you count up the number of occurrences of the number. If it's a standard die, it has a different number on each face. So there's only one occurrence of each number, so the 1 goes here in the numerator. And how many sides are there? 6, and you divide by the 6. Now let's throw a pair of dice. Throwing one die by itself, the probability is just 1/6 for each number coming up. Now you're throwing 2, instead of being a nice, easy transition, and now we've got, 2 over 12 or something like that. Instead, it's very complicated, and that's why I've drawn this whole table to show you all the different possibilities. So here are the different possibilities. The first number might be the one that comes up on the face of one of the die, and the other is the second one that you throw. You're throwing a pair of dice. Of course, you get all these different sums up to 12, starting with 2. So to find the probability of any particular sum, you do the same thing that you did before. You count up the number of occurrences. Let's say you want to throw an 8. So that will give you an 8. That gives you an 8. Here's another 8, and here's another 8. So there's 5 possibilities. And then you divide by all the total number of possibilities, in this case 36. So your probability of throwing that 8 is 5 over 36. If you had a box of 10 resistors and you knew that 2 of them were bad, there's 2 bad resistors in this box, what is the probability of picking a good resistor? You use the same procedure that we did previously. Count up how many good resistors there are, how many chances you have to pick a good resistor, in this case 8, and you divide by the total number of available resistors, which is 10. So the probability is 8 over 10, or 0.8, or 80%. This needs a percent sign on it. I'll put it on there now. And now I want to look at the probability of the complement. What is the complement of picking a good resistor? It's picking a bad one, because those are your only choices, good and bad resistors in this box of 10. Now there's 2 ways to do this. I'll show you that on the next slide. One way to compute the probability of the complement, which is picking the bad resistor, is the usual way. You add up all the number of possible ways this could happen. There are 2 of them. There are only 2 bad resistors, so you put the 2 up here, and you divide by the 10, and then you get again 0.2 or 20%. Okay, just like you did before. Well, the same procedure as before, of course you get a different answer. The other way is to look at the probability of an event and its complement, you can use those two to find the probability of one or the other. And what you use for that is to remember from the lecture notes, hopefully, that the probability of event A plus the probability of its complement is equal to 1. Probability goes between 0 and 1. If you're using percent, it goes between 0 and 100%. The probability of 0 means whatever you're talking about will never occur. The probability of 1 means what you're talking about will always occur anytime you do the experiment. So the reason that A plus A complement is 1 is because that's all the outcomes, all the events of the experiment are covered in A and its complement. So the probability of that is 1. So using that, you can rearrange this equation and find that the probability of A equals 1 minus probability of the complement of A is 1 minus the probability of A itself. Well, A itself was 0.8. We can subtract that from 1 and get 0.2, which is the same answer we got. Now let's look at odds. How do you calculate odds? You hear people talking about odds quite a bit, and this is how you compute them. If you want the odds in favor of event A occurring, this is in favor, you find the probability of A and you divide by the probability of its complement. Of course, you can use this right here, so you don't have to compute the probability of the complement. You can just use that equation. But I'm going to go ahead and use the example above. So the probability A occurred was 8 out of 10. I could have written 0.8. The probability that A bar occurs was 2 out of 10. I want to show this because these are complex fractions, and you might say, I don't know what to do with them. Here's what you have. You've got 8 of 10 divided by 2 out of 10. That is the same as 8 over 10. Now, if you divide, that's the same, well, I'll just write it's a division of 2 over 10 because a fraction is really a division problem. How do you carry out division of fractions? You change it to a multiplication and you flip it around. So the 10s cancel and you end up with, in the room, 8 out of 2, 8 over 2. You don't have to write all this out. I was just showing you how it works. Because if you have the same denominator for these fractions, you can just cancel them. 8 over 2, then which can reduce to 4 over 1, and the events are 4 to 1. Now if you want to find the probability against the event occurring, you just use the same fraction but the inverse of it, the reciprocal of it. You take the probability of A bar and divide by the probability of A. So A bar was 2 out of 10, 2 over 10, and the probability of A was 8 over 10. Again, the 10s cancel, and so that's 2 over 8, which is 1 to 4. I guess that's not a surprise. The probability in favor is 4 to 1. The probability against is 1 to 4. But you might be asked to compute either the probability in favor or the probability of against, and this is how you do it. We'll look at one more topic in this video lecture, and that's the conditional probability, the probability that B occurs given A. So let's do some examples. What is the probability of drawing a red jack, that would be hearts or diamonds, if the jack of clubs has already been drawn? Well, if the jack of, let's look at the denominator. How many red jacks are there in the deck? 2. Does it change if the jack of clubs has been drawn? No, because that jack is black. So there's 2. However, if the jack of clubs has been drawn out of the deck, how many cards are left? There's only 51 left. So there's the probability of event B given that A occurred. This just requires sort of thinking about it. No big mathematical calculation involved. Let's see about drawing a black face card if the king of clubs has been drawn. All right. How many black face cards are there? Well, there's jack, queen, king. So there's 3 face cards in 4 suits. 2 of them are black, so that's 6. There's 6 black face cards. Now you've drawn the king of clubs out of the deck, so you know that the denominator is now 51 because one card is missing. The king of clubs is a black face card, so instead of being 6, there are now 5 of them. Here's the probability of B given that A occurred. What's the probability of B if A had never occurred? If A hadn't occurred at all, it would be 6 out of 52. because there'd still be 52 cards in the deck, and there'd still be 6 black face cards for you to choose from. So this is the end of the first homework help video for Chapter 4 in Statistics.